Okay guys, let's do some problems from chapter 38. So the problems I think we will be doing today are problem 24. I hope that this should not be hard enough for you guys to do. Sometimes the writing and reading the problem will make it a lot easier with my writing pen. So problem 24. The other problem is, this is from the 15th edition, okay? If you have difficulty in finding these problems in the 14th edition, please let me know and I will tell you exactly what they are. Okay, problem 31, problem 35, and even hopefully problem 39, okay, and 39. So these are the 4 problems from this chapter. They mainly deal with 2 ideas. First of all, the Compton effect, and the other one is the photoelectric effect. Okay, so problem 24, it says that if the average energy emitted by a light bulb, basically 120 light bulb, is, if the average frequency emitted by a 120 light bulb, 20 watt light bulb is 5 times 10 to the power 14 hertz, and 10% of the input power is emitted as visible light, approximately how many visible light photons are emitted per second? Okay, here is the idea. You have a 120 watt light bulb. Only 10% of it is in the visible region. I mean, gives you the visible light. Okay, 12 watts visible. So that's basically the power in the visible light that is emitted from this light bulb. Okay, that's the hypothesis of this problem. And now it says that the average frequency F is 5 times 10 to the power 14 hertz, which is in the visible region. Okay, now it should be, at least I didn't really honestly compute this number, but it doesn't matter. We have F. So what's the question in here? Approximately how many visible light photons are emitted per second? So now, if I find the energy per photon, which is equals to, why did I write it as that? It's equal to the frequency times Planck's constant. So this is a single photon. Okay, and I have the frequency, I know what the number F is. In order for me to produce, because this is in 1 second, I have 12 joules, so in order for me to produce 12 joules per second, I need to bring a bunch of them. I need to bring an N of them. So N times this energy per photon, so this is the energy of a single photon, must be equal to 12 joules. Of course, in 1 second, that's what the watt is. So we want the answer is how many photons are emitted per second. So that's how we can find N in here. From N, this expression is 12 joules over 6.626, if you like, times 10 to the negative 34, times the frequency, which is in here, 5 times 10 to the power 14. Okay, if you do the math, so basically, what is it? Okay, you finish the numbers, but I'm going to come up with a rough number in here. 10 to the negative 34 and 10 to the negative 14, that's 10 to the power 20. That's a large number of this. I have in here at the end 12 divided by 5 times 6, that's what? 30. 5 times 6, that's 30, so it's 33. So one of these decimal points moves in here, and now I have 19. So it's of the order of 12 divided by 3, or about 4 times 10 to the power 19 photons per second. Obviously, the task in here is get the real numbers, do the math, do the calculations, and as a matter of fact, also check the solution, because you need to make sure that you're convinced that it is correct. So that's the item that you're supposed to be doing today. Okay, and this is true for all of the problems. So anyway, I just got a rough estimate of 4 times 10 to the power 19 photons per second. At what distance, that's part B, at what distance would this correspond to about 10 to the power 11 visible light photons per square centimeter? This is like the inverse square law. Let me explain what that is. Obviously, if you have a light source in here and you have so much power in here that is emitted, when you move away from it, it's going to spread over a bigger area. So if this distance is r, so it's going to spread over an area of the sphere, because it's in a 3D, 4 pi r squared. Okay, so the intensity in here as measured per unit area, whereas the intensity in here for square meter immediately next to the power source is a lot higher. So the number of photons now are spread thin across this big sphere, and their number now drops to the number that I computed over this big sphere, and this is a number that was given to be 10 to the power 11. Okay? So they want to find r. We just have n, so we can find r as being n, which is 4 roughly. Okay, I know that you guys have better estimates in there. 10 to the power 19 over 4 pi 10 to the power 11 under the square root. The 4 cancels the 4, and I'm left with 10 to the power 19 over 10 to the power 11, which is 10 to the power 8 under the square root. That's 10 to the power 4. Remember, the answer is going to be in oh no, this number is in per centimeter squared. You have to be very careful. This is not per meter squared. So this is the number of photons emitted per second per centimeter squared. That's what was given. So the answer is going to be in centimeter. Okay, so it's 10 to the power 4 over square root of pi, and square root of pi is what, about. Anyway, so again, this is an estimate because this actual number is an estimate, so you better get a better number in here. So it's going to be 10 to the power 4 centimeters divided by 4 by square root of 3, which is what, about 10 meters divided by something. So it's going to be of the order of a few meters away from the source. Okay, so again, this is my estimates. You guys are supposed to come up with better numbers. Okay, so I didn't even finish the calculation, but you're supposed to fix this number first, n, and plug it in here and take the square root accordingly, and you find the value for the distance. It's going to be in centimeter though. Okay, you have to be very careful with the units, otherwise you get some nonsense numbers. Okay, problem 31. So this takes care of problem 24. So problem 31. Problem 31 basically says what you have in this case is a nuclear fusion reaction at the center of the sun produces a ray or gamma rays, photons with the energy of 1 MeV. So the gamma rays that are produced, they have an energy of 1 mega electron volt, or 10 to the power 6 electron volts. Okay, so that's the energy of a photon, of the photon. Okay, by contrast, what we see emanating from the sun's surface are visible light. So basically we are in the gamma range inside the core of the sun. By the time it reaches the surface, it changes the frequency so much that the wavelength now is a lot longer than when we started with, which was for the gamma rays. So by the time it reaches the surface, photons with the wavelength of 500 nanometers. 500 nanometers, put them smack in the middle of the visible light, exactly what we see on the sun. So initially it has a wavelength lambda, okay, and it shifts so much by the time at the end of this one it's going to be a new lambda, which is 500 nanometers. Okay, so this energy in here, I need to know first of all the frequency corresponding to this one, okay, or the wavelength. So this is the energy, which is hc over lambda equals to 10 to the power 6 electron volt, which is 10 to the negative 19, and if I do the calculation correctly, 10 to the negative 19, wait a minute, 1 electron volt, yes, it's 10 to the negative 19 joules. So in other words, this is h, which is 6.6 10 to the power negative 34 times the speed of light, which is 3 times 10 to the power 8 divided by 10 to the power 6, 1.6 first of all, 10 to the power 6 negative 19, that's negative 13, and 13 and 34 gives me negative 21. Negative 21 plus 8 is going to be to the power 13. Okay, negative 13. But don't forget that I have 3 times 6, which brings it to about 20. 20 divided by 6 is about 10 or something like that, or 12 times 10 to the negative 13 meters, or roughly about 1.2 picometers. Okay, 10 to the negative 12 meters. Okay, so this is the initial wavelength. It's this small, and by the time it comes up, it's shifted so much to the point that now we have 500 nanometers. So it has increased so much in length, meaning the energy, the frequency has dropped a lot. So a simple model that explains this difference in wavelength is that a photon undergoes Compton scattering many times, in fact 10 to the power 26 times, as suggested by models of the solar system, solar interior, as it travels from the center of the sun to its surface. Estimate the increase in wavelength of a photon in average. Okay, so on an average, it's going to be delta lambda. So this is the average value. Because I have 10 to the power 26 of them, they all give me a big shift from basically that 1.2 picometers to 500 nanometers. And this is the big shift, okay? So this is the overall shift. It's like traveling a distance, for example, I don't know, I'm just trying to give an example here, from LA to New York, but then you have increments, so that's the overall distance, and this is basically the change in distance, in wavelength in here, to minus the initial one, which is 1.2 times 10 to the negative 12. Up front, I'm going to ignore this term because I'm just getting some rough estimates, and even if probably we put it in a calculator, this would be negligible anyway. So at the end, it's mainly the final value, which is a very long compared to, this is still very small, I mean, because it's a nanometer, but compared to a picometer, it's a lot longer. So at the end, delta lambda is clearly equal to 500 times 10 to the negative 9, roughly, okay, divided by 10 to the power 26. And in here, if I do the math in here, negative 20, minus 26 minus 9, that's minus 35, but don't forget I have two numbers in here, so it's going to be 510 to the negative 33 meters. Wow, this is a very small shift. As a matter of fact, so almost of the order, I mean, it's slightly higher just by than Planck's length, which is about 10 to the negative 35 meters. Okay, there is no point in here. Okay, so don't say that there is this distance is of the same order and somehow we're calculating it. That's not possible. That's nonsense. Okay. Anyway, this is a phase shift. That this is a shift in the wavelength from one value which is very tiny to another that is almost equal to it. It's basically significant. That means that the incoming ray, when it suffers from this Compton scattering, this shift must be so tiny. The angle in here must be so tiny. By the time it leaves, it will be significant, and of course the wavelength will be a lot longer than what we started with. Okay, because the photon will lose so much energy by the time it reaches the surface. Its frequency is a lot less than what it started with in the gamma range. It becomes in the visible range. Okay, part B. So part A, estimate the increase in wavelength of a photon. So this is basically the increase in an average in a photon in a Compton scattering. Okay. So B, find the angle in degrees from which the photon is scattered in the scattering event described in part A. Hint, use for approximation, cosine of phi is roughly equal to 1 minus phi squared over 2. For phi, a lot less than 1, and phi of course has to be expressed in radians. Now the reason why they're saying that is because delta lambda is so small in here, so the phase shift, which is, remember from the lecture, lambda prime minus lambda is equal to lambda e times 1 minus cosine of phi, and this lambda e is actually of the order of 2.4 times 10 to the negative 12 times 1 minus cosine of phi. The whole thing is small anyway, but this one is a lot smaller. It's 5 times 10 to the negative 33. So the negative 33 and the negative 12 is what? Negative 21. So it's still a very tiny number. 5 divided by 2.4, that's roughly 2. So it's going to be 2 times 10 to the negative 21 equals to 1 minus cosine of phi, which is, that means cosine of phi practically equal to 1, which means phi is equal to 0 for all practical purposes. So let's see how much cosine of phi is. So I'm going to use the Taylor expansion that they suggested. 1 minus 5 squared over 2. So the 1 cancels the 1, and we get from this expression phi squared over 2 is roughly equal to 2 times 10 to the negative 21, which puts me at an angle in radians. Phi equals to the square root of 4 times 10 to the negative 21, and that would be the square root of 40 times 10 to the negative 22, because I just want to get this as an even number so that it's much easier to come out of the square root. And phi in radians is equal to square root of 40, which is what, 6, roughly 6 times 6, 36, times 10 to the negative 11 radians. If you care to convert this one into degrees, you multiply the radian by 180 and you divide it by pi. So this is roughly about 180 times 6 divided by pi, and times 10 to the negative 11 degrees now, not radians anymore. So phi in degrees is going to 6 divided by pi is roughly 2, because pi is 3 point something, and 2 times 180 is about what, 3.6? Guys, you need to check these numbers for me, okay? So that is really your task in here. Sorry, not negative 11. I already did the conversion in here, because I have 2 digits in here, they need to move there. So this is negative 9 degrees. So this is the angle, which is a very, very small fraction. It's actually a billionth of a fraction of a degree. Just to show you how small that basically scattering is. Okay. It is estimated that a photon takes about 10 to the power 6 years, a million years, to travel from the core to the surface of the sun. Find the average distance light within the interior of the sun. It looks like this question has nothing to do with the problem, but with the scattering at least. Let's see what's going on. So it takes a million years for light to travel, which is 10 to the power 6 years, and a year is 365 days, and a day is 24 hours, and an hour is 3600 seconds. Okay, so this is how many seconds for light to travel from the core all the way to the surface of the sun. Okay, in doing so, it's going to suffer 10 to the power 26 scattering. Okay, events, if you wish, quantum scattering. So here is the distance from the core. Here is the distance to the surface of the sun, and there are 10 to the power 26 of these collisions. The time between a collision and a collision is t naught. If I add up all of these ones, I will find my big T. So 10 to the power 26 T naught is equal to that T. Okay, from here I can find the time between the scattering, where light travels before basically unimpeded, where the photon is actually traveling, and that is T over 10 to the power 26. Okay, again, you just plug in the value of T from there. Now the distance light travels during that event, so that's what the question is asking. Find the average distance that light can travel within the interior of the sun without being scattered, because all of this time is being scattered. So the only times when it's not scattered is between two events, which are 10 to the power 26 events. So the distance d in this case, remember light is traveling with the speed of light, ct naught. So if I plug in all of these numbers, so it's going to be 3 times 10 to the power 8 times 10 to the power 6, that's a million years. A year is 365 days times 24 hours times 36 seconds in an hour. This is basically the time t, and this is the speed of light, and this is 10 to the power 26. Plug in all of the numbers, I'm just going to get a rough estimate in here again. 8 and 6, that's 14, deducted from 26, that's 12, and I have 1, 2, 3 zeros in here, so I'm down to 9, and I have another one in here, I'm down to 8, and I have 2 in here, so I'm down to 6, and the rest of the numbers, so D in distance is going to be 10 to the negative 6 already, but I have this big number in here that I have to worry about. 3 times 3, that's about 10, times 2.5, that's about 25, 25 times 3.5, 20, let's make it 20 times 40, that's about 80. Obviously you guys are going to come up with a better answer than what I'm coming up with. Better, I mean, you're going to plug actual numbers and see exactly what it is, okay? So this is going to be 8 times 10 to the negative 5 meters, or roughly about 0.08 millimeters, okay? Or 80 micrometers if you care to write it that way. So it's a very, very short distance for light traveling without being scattered. So immediately after it leaves one scattering, it's going to engage in a second one, and so on and so forth. And this is as far as you can see technically, because of the fact that and the sun, inside the sun. So the sun is, and that's exactly what the last point in here, the distance is roughly equivalent to how far you could see if you were inside the sun and could survive the extreme temperature there, as your answer shows the interior of the sun is very opaque, because that's you're going to see a fraction of a millimeter basically, so you're not going to see anything inside the sun. That's basically if you can survive. That's what the hypothesis in the question is. So that's problem 31. You guys have difficulty with it, or you want further explanation or help with the math, with the calculations, please let me know, because I think it's straightforward. Problem 35, I probably need Excel for that. Let me get Excel. Let me pause quickly and get Excel. Okay, I have problem 35 now. Basically I plugged in all of the data. Okay, so what it says in here is that in developing night vision equipment, you need to measure the work function for a metal surface. So you perform a photoelectric effect experiment. You measure the stopping potential V0 as a function of the wavelength lambda of the light that is incident on the surface. On the surface, you get the results. It's very important you keep in mind the units in here when you're plugging stuff in Excel. Okay, so I made sure to write lambda as a measured in nanometers, and I plugged in the values. They're increments of 20 nanometers each, and the voltage stops is a few volts. That's exactly how the table actually in the data shows for most metals, for at least the metals that we have in there. 1 over lambda. The reason why I did 1 over lambda is because clearly, if you see from the lecture, the stoppage voltage, let me go into the notes in here quickly. So this is discussion for problem 35. Okay, so from the lecture we know that EV0 is equal to HF, or HC over lambda minus phi. Okay, so if they gave me lambda and they gave me V0, I better, so if I want to find V0 is a function of lambda, so it's going to be HC over E times 1 over lambda minus, of course, phi over E. And so this will be my y-intercept. If I plot it as a function of 1 over lambda, not lambda itself, because if it's lambda, it's not going to be a linear function. And this will be my slope. Okay? So, and that's exactly how it looks like in here, since all I take is 1 over this numbers. Obviously Excel gives you a bunch of extra digits that are not necessary. If this is correct, I assume that the values in here are actually controlled, therefore they are probably accurate, so these numbers are fine at this point, but these ones are measured, and we don't need to convert or do anything with this one. So all I'm going to do is plot this function as a function of the other one, and that's exactly what this graph is. And I get it the trend line, and I ask it to show me the trend line, and this is the trend line in here. If I can make this one bigger, can I make it bigger? Yeah, let's make it bigger. Let's make it 12. Okay, So you guys clearly see from here that the y-intercept is negative 4.7651. Again, there are only 3 sig figs in here, so it's negative 4.77. Okay, so that is my y-intercept, and that is phi over e. So phi over e is negative this number, and it's in volts. So if I want to find the expression in joules, I have to multiply it by 1.6 times 10 to the negative 19. But if I wanted an electron volts, it's actually negative 4.77. So the stopper voltage in here, what is my notes in here? So it's exactly, so phi is negative, no, it's positive because the negative is included already in the formula, 4.77 electron volts, okay? Because this is an energy. But if I want to find it actually in energy in joules, so I have to multiply it by 1.6 times 10 to the negative 19 joules. Okay. Now the y-intercept from the expression in there, again, you have to be very careful with the units, because I was just making a big fuss over these things are being actually 1 over nanometer. So these are 10 to the power 9. Okay. So this y-intercept in here reflects the fact that 1 over x is actually 10 to the power 9. So when you plug in into this expression here to find phi, let me go back in here, to find h actually, because we know c is given in the problem to be 2.998 10 to the power 8, and e is 1.602 10 to the negative 19. So the fact I use 1.6 is probably not good enough for this problem, because it's supposed to be a lab, data. The fact that it's this way doesn't exclude it from being one of the problems that is potentially in the exam. So this is one of the things you guys know by now that I test on too. So divided by e, so this will be the slope that is given in there. From here, since you have c, you have e, and from the Excel you'll get the slope. You're supposed to find an experimental value for h. Okay, so you're going to have a number that should be roughly 10 to the negative 34 joules second. Okay, so make sure you use the correct SI units to get that number. What is this number? Is it 6.2626, or is it close from it? So this is the theoretical value. This is what it is known. Okay, I looked at this problem, and there is a question that is coming down the road where you're supposed to use to find some frequency or wavelength or something. In that case, you use a known value. Don't use this one that is coming from the experiment. All of this does it, as the question suggests, is just to test your data. You see if you have good enough data or not. So if it's close enough from it, you say, yeah, you know what, it's acceptable. If it's too far, especially the order of magnitude, then you know that this data is bogus. It doesn't mean anything. This is not real, okay? So either you made a big problem in the experiment, or there is something wrong with your data. Anyway, so I assume that you guys can finish this part. Part C, what is the longest wavelength of the light that will produce this photoelectron from the surface? Again, the longest wavelength is the one that barely makes it to the anode when it leaves the cathode. So in this case, what it is the kinetic energy is 0. So in this case, 0 is equal to the energy of the photon, which is hc over lambda. So this is basically the longest wavelength. Shorter wavelength will make it, because they will overpower this phi over e. I'm sorry, this is the energy now, so we don't need an e in here. Okay, that's not voltage anymore. Okay, and if you want to put an e, I have to put an e, and it cancels anyway. So from here, you're going to get the longest wavelength to simply being hc over phi, and phi now is in joule. So you have to use the second number, 4.77 times 1.610 to the negative 19, to get this one correct. So this, you use a known value now. Don't use the one that you measured from the experiment, times 10 to the power 8, that's the speed of light, divided by phi, and phi is 4.77 times 1.6 times 10 to the negative 19, and that will give you the longest wavelength in here. Let's just get an order of magnitude for it now. 34 and 8 is 26. 26 and 19 is 7, negative 7. So we are already in the ballpark. So that means 6 times 3. 6 times 6.6 is about 20. 20 divided by 4 times, or 5 times 1.5 is what? 5 times 1.5 is about 12. So we have 20 divided by 12, which is roughly, I'm going to have it about 1.5 10 to the negative 7 meters, and or roughly about 150 nanometers. Okay, because usually we use the nanometer for the light in here when it's in the visible range. Obviously this is below the and above the visible range. This is in the UV range, okay, so ultraviolet region. It's still, this is the longest wave, so if you really want to have counter scattering, I mean if you want to have a photoelectric effect, you may have to get even shorter wavelength than this one, okay, if they want them to be moving. So that's basically how this is working, but this is the minimum wavelength that you need to get any significant photoelectric effect whatsoever. Okay, see, this is in the UV, I believe. Okay, so what wavelength of light is required to produce photoelectrons with kinetic energy 10 electron volts? Except now they are not coming with zero velocity, so they're coming with 10 electron volts. So they're coming with 10 times 1.6 times 10 to the negative 19 joules. That's their kinetic energy, is equal to hc over the lambda. So we need to find this lambda in here, minus phi, and phi is 4.77 times 10, 1.6 times 10 to the negative 19. Okay, so you move this number to the other side, it's going to be positive. 4.77 times 1.6 is roughly about 12. 12 times plus 10, that's about 22. 22 times 1.6 times 10 to the negative 19 equal to hc over lambda. What was the other number in here that I used for this value? I'm trying to see if I can get some close enough numbers for it. So c is going, lambda is going to be hc over lambda, which is 22 times 1.6 times 10 to the negative 19. Okay, 22, how is it related to 4.77? It's about 5 times, okay? Slightly more than 5 times. So the wavelength should be roughly about the fifth of this number, which is about, okay? I'm trying to get, of course you guys still are responsible for this one, which is a lot more energetic, a lot shorter wavelength than this UV rays. Okay, obviously this is much more intense radiation in here with higher frequency, shorter wavelength, so it's going to produce electrons that are not only going to make it to the anode, but they make it with speed, and this is their kinetic energy, 10 electron volts. Okay, so that's problem 35. Let's look at problem 39. For problem 39, this is actually a problem. What it tells you is, so we did all of this for 3 problems. Problem 39, it tells you that you have a photon with wavelength lambda is incident on a stationary particle with mass big M, as shown in the diagram. So the diagram is showing you're showing you a wavelength in here of wavelength lambda, and it comes in and basically hits a particle of a given mass M, and then this is the before. After that, the collision, what happened in this case, first of all they tell you the photon disintegrates, it's gone. Okay, the photon is annihilated, while an electron positron pair is produced. The target of the particle moves toward the right. So basically this is the situation in here. So you have an electron moving in one direction with the, and you have a positron, which is actually a positive electron, moving in the opposite direction. So this is E plus and this is E minus, and then the particle M starts to move also in this direction. They tell you to use specifically V for this symbol for the velocity. V by symmetry has to be also in magnitude equal to that, and this is the velocity of the particle M. This angle is phi. By symmetry this also must be phi. Okay, please don't confuse the phi's. Okay, there are so many phi's in the problem. Okay, there is the phi for the stopping, for the work function, and there is a phi for the scattering in this case. Okay, so there is an angle and there is actually another one which is energy. Okay, so please don't confuse these two phi's in this several problems in this chapter. So the electron travels with a speed v at an angle phi with respect to that of the direction. Owing the momentum of conservation, the positron has the same speed as the electron, so the two have the same v, using the relation, the notation. So this is what they tell you to use, okay? Gamma as being 1 over square root of 1 minus v squared over c squared. As a matter of fact, I'm going to write beta now, write it in terms of beta 1 minus beta squared, where beta in my notation is simply v over c, okay? And then they tell you for the particle m, use the symbol gamma m, just to distinguish between that of the electrons, divided by square root of 1 minus vm squared over c squared. As a matter of fact, I'm going to write it as 1 over square root of 1 minus beta m squared, where my beta m by definition is going to be vm over the speed of light. So that's basically the notation I'm going to be using in this. You write a relativistic expression for the energy conservation in this process. Use the symbol m for the electron mass, okay? So the electron mass. So what's happened before? Before, all I have the energy of the photon and the rest energy of the particle m. But then now, when they are moving, I don't have the photon anymore. I have the energy of the photon, which is basically the total energy. I mean the electrons, the two of them, and they are by symmetry moving with the same velocity. And they have the energy also of this particle m. In this case, also it's its total energy. So initially, before the collision, the energy was simply equal to the energy of the photon, which is hc over lambda, its wavelength, plus the rest energy in this case of the particle m, okay, which they didn't tell us what it is now. Now I have two basically particles with the same mass m, and they have the same velocity, so they have the same Lorentz factor gamma times their mass times c squared. So that is their total, times c squared. That is actually their energy, plus the energy of the particle m, and they tell us to specifically use relativity in this case, gamma m times the mass times c squared. So this is basically, in a nutshell, the conservation of energy for the system. Relativistic expression for conservation of energy in this collision. Now they also, that's part A. Part B in here, they say that write an analog expression for momentum conservation. So we need to write the same thing for the momentum. And the momentum, the particle m was not moving, so the only momentum I have before the collision is that of the particle. And the momentum, remember, from lecture is going to be equal to h over lambda. Okay, so that is the momentum of the photon, must be equal to the momenta. Now I have to look at the geometry a little bit. By symmetry, the momentum in the y direction is 0, because initially we had no momentum in the y direction, and it has to be 0. So the fact that both of these photons, first of all, this one has no momentum in the y direction, so it has momentum only in the x direction. These two have similar momenta. One of them, the component is moving this way, the other component is moving this way. So the only thing that is going to survive this expression, and this is in the x-axis, by the way, and so is the component of the momentum for the particle m in the x-axis, and the x component, basically the projection of this momentum in the x direction. Normally this is a vector, so I'm going to already write it in the x direction. So for this particle, first of all, big M, it has a gamma factor gamma m, Lorentz factor gamma m. Its mass is m and its velocity is v. So this is the classical momentum times gamma. That is for that particle in the x direction, and that's the only component. For the other two particles, by symmetry, they are equal. So I'm going to take two of them, and each one of them has a gamma and an m. Sorry, this is vm times a v, which is the velocity of them. But now I have to take the components, and the component in the x direction is a cosine of that angle phi. Okay, so that is the expression of the momentum in here in terms of gamma, m, and lambda, and everything else that was given in this problem. So this is conservation of momentum. Conservation of momentum in x direction. Okay, so we're done with part B. Part C. Eliminate the ratio h over lambda between the energy and momentum equations to derive a relationship between v over c, vm over c, and phi in terms of the ratio of m over m, keeping gamma m and gamma as useful shorthand notations. Okay, so basically solve this system by getting, so multiply this expression by c and this one and add or subtract the two, or sub it in that expression. That's the same thing. So first multiply by c and add it. So if I multiply this by c and replace in that expression, this is how this look like. First of all, I have gamma m vm times c plus 2 gamma mv times c times cosine of phi. That takes care of this term from the energy. I have to add to it mc squared and equate it to the second half, which is 2 gamma mc squared, 2 gamma mc squared, okay, plus gamma mc squared, okay. So that takes care of this expression. So that's basically, we need to do some simplifications in here, because this is, first of all, I'm going to use my betas now. So V is beta times C, and Vm is beta m times C. So this looks like it's a gamma m beta m C squared plus 2 gamma m beta c squared, because there is a c in here. So I have a cosine of phi plus mc squared is equal to 2 gamma mc squared plus gamma mc squared. As you probably have noted, the reason why I did that is because I want to get rid of the speed of light in here in this entire expression. I'm just dealing with, so the speed of light could have been 1 for all we care, okay, from this expression. I have to group terms in here because they want it specifically in the ratio of m over m, so I'm going to divide by big M in here. So what I'm left with is gamma m times beta m plus 2 gamma beta m over m cosine of phi plus 1 is equal, because they're divided by big M, by the way, 2 gamma m over m plus gamma m. Okay, looks like I have terms that involve gamma, and they are these two terms. This involves gamma m, these two terms involve gamma, and there is a 1 by itself. So let's move everything one side or the other and leave the m intact in here. So I have the 1 intact, so I have a 1, which I'm writing it first, plus, if I do that, I have gamma m, beta m minus 1, which doesn't make sense. We usually, beta m is less than 1, so we can't, so I have to write minus gamma m times 1 minus beta m. That's that. Plus, I have in here a cosine of phi, though, times beta, and everything else is the same. So again, for the same reasons, I'm going to write it minus 2 gamma m over m times 1 minus beta cosine of phi is equal to 0. So that is the expression that they want us to write, because they want us to derive a relationship between v over c, which is beta, and vm over cm, which is beta m, and phi, and we have phi in that expression, in terms of the ratio of m over m, okay, in terms of the ratio of that. So everything is in this expression, and this is the expression they want. Now, consider the case when Vm is a lot less than the speed of light, and use a binomial expression to derive an expression for gamma m. Okay, to the first degree in Vm, use the result. Okay, so when Vm is a lot less than C, that means beta m is a lot less than 1. That means gamma m, which is actually the 1 over the square root of 1 minus beta m squared. If I use this one, it's roughly, Taylor series is 1 minus beta m squared over 2, which is roughly 1 plus beta m squared over 2. Okay? That is the Taylor series. Otherwise you just take the function in here, take its first derivative, you're going to end up with the same expression here. So that is gamma m. So we're going to plug it in here and use that result to, what did they say in here, so basically when Vm is not moving relativistically, it's moving with very slow speeds. Okay, use that result to rewrite your previous result for Vm and in terms of C, Vm over m and phi. Okay, so we basically plug into the expression, first expression, and now we have 1 minus, this term is 1 plus beta m squared over 2 times 1 minus beta m. Okay? Minus 2 gamma m over m times 1 minus cosine, beta cosine of phi is equal to 0. Okay, the purpose of this exercise 2 in here is to note the following. If I multiply these two terms, I have 1 times 1, which is 1, but I have a quadratic term in here, a beta m, and I have a linear term in beta m. So just to keep the leading term, this term is going to be ignored, so basically I will be left with 1 minus beta m. And the 1 cancels the other 1, so, and the minus becomes positive, so if you guys are following, so this should be beta m. That's all that survives from these three terms, from this one and that one, minus 2 gamma times m over m times 1 minus beta cosine of phi. This I cannot do much about, it is equal to 0. Okay? So in other words, beta m is equal to 2 gamma m over m times 1 minus cosine, beta cosine of phi. Okay? So is there a way for beta m to be 0? I mean for Vm to be 0. If Vm is 0, that means beta m is 0. That means 1 minus beta, which is V over C cosine of phi, is 0, which means that if I move this to the other side, V, which is equal to C over cosine of phi. Okay? Obviously, this is more than C, because cosine of phi is less than 1. Cos of phi is less than 1 in general, less than or at most equal to 1. So when you invert it, it's greater than 1. So 1 over cosine of phi is greater than or equal to 1. That means V is greater than or equal to C, and this is not possible. Nothing can reach the speed of light except light itself. And since the particle m has a finite mass m, so this is not possible. So there is no such a way that the mass m can stay stationary. That's what this basically says. You cannot have this situation. This is a no-no. So the answer to the question is, can we ever have Vm equal to 0? No, because then the two electrons must be moving with speeds faster than the speed of light. Suppose the target particle is a proton. Now we know what m is. If the electron and positron remain stationary so that V is equal to 0, with what speed does the proton move? So basically we're going to go back into the original expression, which is this one, and put beta now is equal to 0, because both the proton, positron and the electron come out with a speed 0, and gamma would be exactly 1 in this case, because it's 1 over square root of 1 minus 0 squared. So in this expression, I'm trying to find what gamma m is, and from here, or solve for beta m as a matter of fact, and from here we're going to get the following expression. So we're going to have 1 minus, again, let me go back in here and hopefully you guys see exactly what that is. So we're going to have a gamma m in here times 1 minus beta m in here minus 2 times m over m. We know the ratio of the two masses, times 1 minus 0. So it's going to be just 2 times m over m. Plug into this expression and find the value for beta m. Remember, gamma m is equal to 1 over square root of 1 minus beta squared. So if I multiply this by 1 minus beta m, this is beta m by the way, is going to be just the square root of 1 minus beta m over 1 plus beta m. And if I do this calculation, find the solution to this equation, which is going to be easy then, because I have 2 times this m over m, and this m over m is a very tiny number, so if you care to leave it there as a matter of fact, because it's important. If you don't leave it there, you're going to get a value that is exactly 1, okay? That is nonsense, okay? That means that even the proton is going to be not moving. So you're going to solve this equation, which should be as 1 minus this term now that I just wrote, square root of 1 minus beta m over 1 plus beta m. Again, if you have difficulty with this expression or anything, please let me know. Minus the ratio, 2 times the ratio of the electron mass, which is 9.1 times 10 to the negative 31, divided by 1.67 times 10 to the negative 27. And that is equal to 0. From here you're going to, because gamma is equal to 1 and beta is equal to 0, so it doesn't matter what the angle phi is in here. So at the end you're going to find the value, which is very, very close from, I mean, it's going to be not too fast, okay, very, very small compared to the speed of light, okay? So that's, I'm assuming that you guys can finish the algebra there, because that's part of your duty in here. And part G, if the electron and positron each have a total energy of 5 mega electron volt and move with an angle phi is equal to 60 degrees, then what is the speed of the proton? Okay, I need to find gamma first for the electrons, okay, because I know its their energies is 5 mega electron volt, okay. So in this case, I know that this energy is equal to 2 gamma. Of course, make sure you convert to the proper units, times mv squared, mv, I'm sorry, yeah, mv squared, I'm sorry, what am I talking about in here? I'm trying to do the things, mc squared, man, okay. So from here, you have the mass of the electron, the speed of light, this is each one of them, so you don't need a 2 in here, because each one of them has a 5 electron mega electron volt. They're not combined. So you can solve for gamma from here. Make sure that you use the correct units in here. So you find the value for gamma, which is probably going to be relativistic, okay? It's going to be a very high value, in other words. It's going to be about 10 or 12 or 13 or something like that. Then after that, it's a number with no units. Once you find the value of gamma, that's what they tell you. First, solve for gamma. Once you find gamma, you can find V. Remember, 1 gamma squared is equal to 1 over 1 minus beta squared. So you can solve for beta. So we're going to find the value of beta, which is very close from the speed of light. And so then what is the speed of the proton? So you can find V. So basically, once you find gamma from this expression, you're going to solve for beta, and once you find beta, you're going to find the value of C. What is the energy of the incident photon in this case? So we know now all of the energies, because we can go actually and find the energy of the proton too from this expression in here, because we find gamma, we find beta, we know what phi is, it's 60 degrees. They tell you specifically the ratio of m over m. So you actually can use the same expression, except now on the other side is not equal to 0, but rather it's equal to this number, and you're going to solve for gamma again, gamma m, and it should be non-relativistic. Once you have that, you're going to just go back to the conservation of energy in this case, okay. But this term actually is going to be a classical term, because that's going to be the plane kinetic energy in this case, and basically you find everything in here and you should be able to finish the problem. If you have difficulty with this problem, it's almost an hour. Please let me know. I should actually give you the solution to straight out. Thank you.